Finally, let's look at the motion task section, where the core programming happens. The drive has 32 motion task slots, numbered from ID 0 to 31. Let's look at the setup. The most critical setting here is the type of motion. If you select the wrong type, the system might skip the task, the rotation direction might invert, the motor might overshoot its targeted position, or it might not start at all. First, I will explain the theory behind each motion type, and then I will show you a practical example for each one. In this table, you can see 0 absolute. How it works? It calculates a fixed position based on the parameter machine home 0 baseline. It does not care where the motor currently is. It always goes to the exact coordinate. Best use case, perfect for rotating index table or tool changes where you need to point to exact fixed angles like 90 degrees, 180 degrees or 270 degrees. Why it causes errors? If the motor is far away, say at 1 lakh at position, and the next task tells you to go at absolute 5000, the motor will violently reverse in direction to run all the way back to the old spot. Related to the command position, how it works? It takes the drive's current ideal theoretical target and simply adds your specific desired distance to it. Best use case, great for standalone single step movement that start and stop completely on their own without blending into the other tasks. Why it causes errors? It causes F6004 errors during high speed bending. This happens because the drive checks the target register before the previous movement math has fully finished setting down. Relative to the previous targeted position, the magic mode. How it works? The mode strictly adds your distance to the exact mathematical endpoint of the task right before it. Best use case, excellent for continuous multi-segmented moves where the motor needs to shift speed or change profile smoothly without stopping. Why it's great? It eliminates blending errors completely. It locks the background pipeline math so tasks can't skip or misalign directions mid-fight. Related to the external position, how it works? It ignores immediate position math and wait for the physical sensor like a photo eye sensor to trigger it. Best use case, used in a conveyor product alignment, labeling machine, or packaging lines where cut or label must happen the exact millisecond a sensor sees a product edge. Why it causes errors? If the motor hits its safety travel limit before the physical sensor gets tripped, the driver will fault out instantly. Related to the feedback position, how it works? It adds your distance to the raw live encoder sensor value at the exact millisecond it triggered. Best use case. You should only use it for the slow manual help or calibration adjustment when the motor is completely standstill. Why it causes errors? It causes massive skipping and glitches during the high speed blending. Because of the microsecond sensor lag, the live recording changes too fast, which continuously wrap the calculated destination. Now that you know how each motion type calculates its path,